Okay, previously we saw this section of this chapter 6, and this section 6.1 is about basic counting methods. Basic, just fundamental. For example, the product rule, we started with the product rule, and then we went on the sum rule, and then similarly, subtraction rule, division rule, and some tree diagram. So these are the things that we saw in the previous lecture. Now we are going to start with the pigeonhole principle. The name is just a frightening name, but actually there is nothing in this topic. It's a simple. So don't be afraid from this name, pigeonhole principle, okay? So what is this pigeonhole principle? He's saying that if you have the K boxes, and if you have to place K plus 1 or more objects into these K boxes, where K is what? K is a positive integer. So if you have the K boxes and you want to place K plus 1 or more objects into it, then okay, the K objects, one object in each box, you until you have the K boxes, okay, the K objects are now placed, okay. But what about the K plus 1? What about the extra one? You can place that extra one in any of these K boxes, and when you will place it, then in that box there will be two objects, okay, two objects. So this is that statement is saying that if you have the K boxes and if you want to place K plus 1 or more, I have just given an example of only one extra object, but you can take 2, 3, 4 more, and then you can place one more in that box, one more in that box, and so on, and so on. You can go like that. Then there is at least one box. So there would be one box if you will place these K plus 1 objects into it. Then at least one box would be like that, in which you will have 2 or more objects. Okay, no issue. This is a simple statement, and this is a statement of this theorem, okay? So then there would be at least one box, at least one box. More boxes are possible. More boxes are possible, but at least there would be one in which you will have 2 or more objects. Okay, this is what we have seen here. So this is the statement of the pigeonhole principle. And okay, this is the name of that person, Lejeune de Richelieu. So this is the German mathematician. So who gave this statement, who gave this theorem? The other name for this theorem is Dirichlet-Dreyer principle. Now we are going to see the example. For example, if you have English words and if you have 27 English words, for example, this is one word, begin is one word, with is another word, these another word, same is. So for example, I'm just saying what is one word. Minimum is also English word, number is also English word. So if you have 27 English words, then by using this concept of theorem, you know that 26 is the size of the alphabet set of the English letters. 26. And if you have 27 English words, then what is the possibility according to that statement? The possibility would be that if each name is different, then the 26 English words in these 27, 26 will cover all the letters, and the one extra, that would be the repetition. That can start with any existing 26 letters. So he's saying that at least 2 English words will begin with the same letter. Okay, Yeah, no doubt. This is according to that statement. This is according to that pigeonhole principle. 20, 26 would be of 26 English words will start with the different English alphabet letter, and the 27th would be again just a repetition that can start with A or B or C or D or whatever. But then at least then we can say that at least two words will begin with the same letter. Okay, that is the example of this pigeonhole principle. And now you have another theorem, theorem 2. Now we are going to make this statement of theorem 1 more general. More general. In this statement of theorem 1, we are talking about k plus 1 objects. But here in this theorem 2, we will not talk about k plus 1. Rather, we will talk about n objects. Okay. Now you have to place n objects into k boxes. And k is what? K is similar, positive integer. So now you have to place n objects into k boxes. For example, your objects are, for example, 21, and your boxes are, for example, k is 5. 21 and 5. So then there is at least, this is the condition. Then there is at least, more is possible, but at least one. Then there is at least one box that will contain n divided by k and the ceiling function. You know that this is what? This is what? Ceiling function. This is called ceiling function. So n is 21 divided by k, k is 5. So 21 divided by 5, you will have 4.2 something, 4.2 something, the answer. But this ceiling function will give you what? If you have the answer 4.2, this will give you 5, yes. This is the ceiling. When it will give you 5, now you can understand this statement, what this statement is saying. What this generalized pigeonhole principle is saying. This statement is saying that if you have 5 boxes, okay, if you have 5 boxes, okay, and you have 21 and you have 21. So what will happen? 1, 2, 3, 4. So 4.2. So first you will have 4 objects in all these boxes. When you will have 4 objects in all these boxes, then it will become 20. But now your n is 21. So 1 extra. So you can place that 1 extra where? In any box. And if you will place that 1 extra here, then this will contain what? 5. That is what? 21 divided by 5. 4.2, and ceiling function will give you what? 5. So that 5 objects. So now n objects are placed into k boxes. When you will place them, at least there would be 1 box. All are possible, but at least now you have at least 1 box. 1 box in which you will have n divided by k objects. Now you have those objects here. So this is the statement of the theorem 2. This is the statement of theorem 2. Example 6. Here we have the question, and then we have the simple solution. What is the question? What is the minimum number of students? Have I started the recording or not? Thank God. It's going on. Okay, what is the minimum number of students? Minimum number of, at least. Minimum means at least. What is the minimum number of students required in a discrete mathematics class to be sure that at least 6 students in that class will receive the same grade? And if there are 5 possible grades, what are the possible grades? 5, A, B, C, D, and F. And the question is, what is the minimum number of students in the discrete mathematics class to be sure that at least six students, this is the condition. At least six students will get the same grade, We don't know the strength. This question is asking about what is that minimum total number of students in the class. Then that if you have that strength in that class, then finally you can say that okay, now the students will such number of students will get at least this same grade. So you have to think in that way, either theorem 1, either theorem 2. So at least 6 will receive. So when you will have at least 6, this is that condition, at least one box containing the objects, this one, or at least one box containing 2 or more, this one. Anything is possible. So at least 6 will receive. So it means that here you will have one extra. In this box, you will have one extra object. And here in this box, you will have one extra object. This was the definition for theorem 1. This was the definition diagram for the theorem 2. So at least, if it is at least 6, then it means 5 is available. 5 is the number of students for which or for them grade is surely the same. So now here 1 5 here, this is the answer. This green one is the answer. Rest is not needed. And I am explaining this 5. You can say it. This is the number of grade 1, 2, 3, 4, 5, and 5. A, B, C, D, and F. Okay, these are the 5 grades. And this 5 is the number of students. Or you can change, no issue. And this is called product rule. What product rule? That's that product rule that you have seen here. Multiply that thing and you will have your answer. So first you have to calculate the number of students. So that's why we are multiplying 5 number of students with 5 grades, and then it will become what? After product, you will have 25. But you want what? At least 6 will receive the same grade. So according to these theorems, put one more, and okay, that is that additional extra student 1. That one is one extra additional student. And that student can be in the box of A's or B's or C's, any box. And these boxes are what? 5 students are getting A, 5 students. This 5.5 means what? 5 students are getting A, 5 students are getting B, 5 students are getting C, 5 students are getting D, and similarly 5 F. And when you will sum up all these students, it will become 25. And now you have one extra. So you can place that student in any of these boxes. And if you will place them in A, okay, then this box will contain how many? 6 and rest, and the remaining and the others will contain only 5. But the total number of students would be 25 plus 1, 26. That is the at least condition. At least. More is possible. More is possible, we know that. But this is the at least condition according to that theorem. And this 26 is the answer of this example 6. Okay. So the minimum number of students needed for this class is 26. Is 26. Moving on. Theorem 3. This theorem has some statement, and that statement is saying that every sequence, what is sequence? Any, for example, previously, for example, you have seen previously in some CO sequences. I don't know which one is. Okay. You maybe the previous one. I'm an old man, you are a young boy. Now uh, you have to remember that when we studied that topic. So we studied somehow sequences somewhere. Yeah. And then you can say, for example, and there is a one sequence like that, one which is 2 raised power 0, and then 2 raised power 1, 2, then 2 raised power 2, 4, then 2 raised power 3 is what? 8, and so on. So this is sequence. So this is sequence. I'm just reminding so that it would not be an issue for you. So every sequence of n square plus 1 distinct real numbers. Every sequence which is the sequence of real numbers which will have distinct means different, n square plus 1. This is, by the way, here according to that statement, it is saying that this sequence will have this number of real numbers in it. But this is also a format for this sequence. Okay, let's see. But actually this is some real number which is giving the size of the sequence, which is giving the total size of the sequence. So every sequence of this size will contain a subsequence. That sequence will have some subsequence, and the length of that subsequence would be n plus 1. And if it is the situation, then that subsequence will either have strictly increasing property or strictly decreasing property. Statement is now completed that every sequence which have this size, then that sequence will contain some subsequence of size n plus 1. And if this is the situation, then that subsequence will have, or you can call that subsequence either a strictly increasing subsequence or strictly decreasing subsequence. Increasing means when their elements are in increasing order. For example, here 1, 2, 4 are increasing order, and decreasing is the opposite. And strictly decreasing is the opposite, in which you have the higher number first, lower numbers after. So that is the definition for strictly increasing or decreasing, nothing else. Okay, so this is the theorem, and now we have the example. For example, here we have the sequence 8, 11, 9, 1, 4, up, and so on. So this whole green area, this is the sequence, and it contains 10 terms. So this is the size, 10 terms. This is a size. Now we can, first we want to convert this size according to that theorem 3. So now 10, this 10 terms is equal to 3 square plus 1. Can I write like that? Can I write 10 like 3 square plus 1? 3 square is what? 3 3s are 9 plus 1, it would become 10. So 10 equal to 10. So now I can write this size of that sequence like that, which is the format of this theorem 3 for a sequence. Okay, we can write. And if we can write, then we will have some subsequences in the sequence of length n plus 1 or any length. And those subsequence will have that property of increasing or strictly decreasing type thing. For example, here there would be two, four subsequences. Now these are the subsequences of this bigger sequence, but these subsequences have the property of strictly increasing. 1, 4, 6, 12. 1, 4, 6, 12. 1, 4, 6, 7. 1, 4, 6, 10. So we extracted these subsequences from here. And the elements are the terms in those subsequences are in strictly increasing order. And similarly, we have a sequence 11, 9, 6, 5 from this bigger sequence, but this subsequence has the strictly decreasing order. And length of this subsequence is 4. And also here we have the 4. And this, when we converted this 10 into 3 square plus 1, then this is 3 square. So this 3 is taking the place of this n. So now my n is here, now my n is 3. And subsequence of length 4, 3 plus 1, 3 plus 1, 4. So that's why I have taken these subsequences of length 4, okay? We have not taken of length 5 or 6 or whatever. We have taken according to that formula, nothing else. Okay, example 13. Assume that in a group of 6 people, you have 6 people, and each pair of individuals, and if you will make the pairs of these 6 people, means 2 people in a pair, each pair of individual consists of, then though that pair will have either 2 friends or 2 enemies. So of 6 people, you can make maximum how many pairs? Maybe 3. And then each pair, either those 2 members would be friend of each other or would be enemy of each other. This is the assumption. This is the assumption. You have to assume like that. So for example, if 2 people are friends, and in the next pair, if 2 people are friends, okay, then now we have 4 friends. And in the next pair, you have again friends, then we have 6 friends. We can stop here, then we will have 4 friends. We can stop here, then we will have only 2 friends, and the next are enemies. So many possibilities. But this is the assumption. This is something we are assuming. Question is, show that there are either 3 mutual friends. Show that there are either 3 mutual friends or mutual enemies in this group of 6 people. Question is, show that either there are 3 mutual friends or 3 enemies. So for that, we are taking some person A separate from the 6 people. We are taking out one person from that 6 group of 6 people. And that person which we are taking out is A. And then after that, the remaining people would be 5, okay, in the group, would be 5 in the group. Now in these remaining people, 5 people, now it can happen that there would be either 3 or more who would be friends of A. So this can be happen according to that assumption. According to that assumption, in these 5 people, 3 or more can be the friends of this A, or 3 or more can be the enemies of A. We only have to show that either 3 mutual friends are possible or either 3 mutual enemies are possible in the group. So you can use simply generally the generalized pigeonhole principle, this one, second one, and you can use this formula. And what is my n now? The remaining n is now 5. And what you want to do, you want to either calculate friends, 3 mutual friends, or 3 mutual enemies. You want to decide about the 2 sets, nothing else. So that's why 5 is your n. and K is your two sets that you want to build, one for friend, other for enemies. After division and with the ceiling function, what you will get? You will get 3, because it is 2.5 something, and then it will give you the 3. So that is the mathematical proof that you have 3. Either friends are either these 3 are either friends or enemies, whatever it is, but you have that number. So that is the answer of this question. Show that. So now it is shown. But this is now next. You can just do the theoretical discussion if you want. Otherwise, the question is ended here. In the former case, now there are two cases. The former case is the case of friends, and the later case is the case of enemies. Former means which is coming first. So this green was the first case we mentioned here. So this is the case of friends, and this yellow is the case of enemies. This is the later case. So now we have 3. We have answer from this generalized pigeon principle. We have 3. So we can consider 3 persons. So now for the former case, for the first case of friends, we can suppose A is already taken out. So then B, C, and D, we are just supposing that the B, C, D, these 3, we are supposing that this 3 is B, C, and D. And we are supposing that for this first case that they are the friends of A. And if any of these 3, from these 3, B, C, D, if any of these 3 individuals, if 2 of them are friends, then that 2 and A itself, they will again form a group of 3 mutual friends. And if this is not the case, then B, C, D are friends with each other, but they are not friends with the A, so they are the mutual enemies of A. And similarly, you can go on with the discussion like that for the enemies. Here we have these 2 sentences for the friends. You can just write the same sentences again for the enemies. And these are some examples mentioned here from the book that you have to read and understand. Moving next to the section 6.3, which is about permutations and combinations. Most of the time, people considers permutation and combination the same thing. Actually, their concept is same, but there is a difference between them. And that difference is that in permutation, the order of the elements are the terms matters. In permutation, the order of the elements are the terms is important. And in combinations, the order of the terms are the elements is not important. This is the difference. Otherwise, they are just like a list or just like a set having elements in it. So permutation is what? The definition is ordered arrangement of elements or objects is called permutation. When you have the order. When order is important, then that is called permutation. And that would be arrangement of objects or terms or elements of a set. And from that set of permutation, you can take a small portion of that permutation. And if you will take that small portion, you can call that R permutation. You can call that R permutation. R would depict the number of the elements in that small portion. R will represent the number of elements or the terms in that permutation. For example, here, if we have the set S is equal to 1 to 3, and then if we have taken some arrangement from this permutation like that, 3, 1, 2, 3 first, 1 in between, and the 2 at the end, if this is the order of the arrangement of the elements you have taken out from that permutation, so this is, then you can call it, it is a permutation of this set S. And when we are saying that, the order that we have here, 3 first, 2 at the end, so it is important. It is important. If you will change the order, 1, 3, and 2, then that would be a different permutation, not this one, okay? Not this one. Because order is important. And similarly, if you will take out 3 and 2 from this set, and also with some order, 3 first, 2 after, this would also be called permutation. But here you have the 2 elements, so that's why you will call it 2 permutation of this set S, in which you have only 3 elements. So now you have the concept of permutation, and our permutation is clear with this example. Theorem 1. This theorem 1 is about this concept of permutation. And this is saying that this is the equation of this theorem, which is important. And this is saying this R is the R like that, R permutation, okay? And this N is the, you can say, total number of objects available in the set. So then this P means permutation. P and R, what it means? It means, how you can read it, R permutation of N objects of a set. Okay? How you can read it? R permutation of N objects of a set. And how you can calculate that R permutation of N objects of a set, the right hand side will give you that answer. You have to multiply their, okay, you can say permutations. You can start with N permutations first, then N minus 1 permutations, multiply with N minus 2, and so on, N minus R plus 1 permutation. Totally, these are R permutations. And you have to multiply them. You have to multiply them. And what is N? What is R? N is a positive integer. R is what? Is an integer. It is between 1 and N, which means greater than or equal to 1, less than or equal to N. And this is something, the equation. Now you can call it R permutations of a set with N distinct elements. Okay, this is now the theorem 1. And now you have the understanding of this equation. Now we will apply this equation to calculate different things. For example, we have an example here. And what this example is saying, how many ways, how many different ways are there to select first prize winner, second prize winner, third prize winner from 100 different people. From 100 different people who have entered a contest. And these 100 people have entered in some competition. And you want to calculate that how many different ways are there to select first prize, first winner, second winner, third winner, from these 100 people. And this R permutation of n objects, it is what? It is R number of ways to do the thing for the n number of elements in that set. Permutation is also different representation, different representation. Combination is also representing different ways to represent elements of that set. So now this example, for when you have this question, how many ways? Then according to this chapter, we are in this topic, so that's why now you have to think in that way. Otherwise, you can think the product rule, the sum rule, the division rule, what are the others that you are learning one by one. The only thing is that you have to identify what type of situation it is. And this is what you will get through experience. When you will do the exercises again and again, then at some point you will have that experience built in your mind, and then you will identify that here what type of thing you can apply. So if you want to solve this example using this theorem 1, then you need what? We need n and r. We need n and r. What is n? N is the total number of objects. Here 100 different people is total number. This is for n, it is easy to identify. And what type of permutations you want? First prize winner, second prize winner, third prize. So 3 things you want. So you want to identify 3 permutations, okay? What do you want? 3 permutations. Your R is 3, your N is 100. And then you can put it into that formula. P 100, 3. Okay. Then start with this n. N is what? 100. Okay, n. And then multiplied with n minus 1. This n is 100. Minus 1, you will have the 99. Multiply with n minus 2, you will have the 98. And this is what? You have to stop here, because 3 permutations. Only 3 permutations. This is 1 permutation, 2, 3, and so on. So stop it now, because you have to calculate only 3 permutations. And then after multiplication, you will have that answer. And that answer is the answer that these are the different ways which, these are the number of ways which you can use to select first, second, and third prize winner from these 100 different people. And there is a corollary 1. You can just read that, n factorial divided by, and what is this saying? You have the formula here, but you also have something, a formula for permutations like that. So what is it is saying? R permutations of n objects in the set is equal to n factorial divided by n factorial minus r. Okay, let's see if you will do that. If you will write these values here, here you have the 103. So 100 factorial divided by 100 minus 3, which is what? 97. 97 factorial. So, okay, that is also working. I think that is also working. 100 factorial and divided by 97 factorial. It means that 97 will be cancelled. And then you will have this thing remaining. And this is the answer you have. Now moving on. Example 7. How many permutations of this letter A, B, C, D, E, F, G, H contain the string A, B, C? So these are the eight letters, 8 different letters. And how many permutations of these letters? And we want to move these letters here and there, but we want to keep this string ABC as it is, as a block. We don't want to change the order of these A, B, and C letters, okay? We can shift this ABC here. We can shift this ABC maybe here, any position, but we will shift the whole ABC, not A only, not B only, not C only. So that ABC will move as a whole block. So how many different ways are possible to change these different letters with each other in position wise? How many permutations? So, okay, this ABC is one block. And then what are the letters remaining? 1, 2, 3, 2, 3, 4, 5. 5. 5 is remaining. And this ABC is a 6th one. And now you have the 6 different positions. So simply 6 factorial, you have 620 permutations. It's a simple one, so I'm just moving to the next definition just to save my time, because there is some topic at the end which I want to cover essentially. Okay, so these are the things which I want to cover compulsory. Now, so there are 6 different positions. So then you can do what? So the first is, okay, 6, then multiply. After fitting that position, then you have the 5 positions left, then you have the 4 positions left. So that is what you are doing here, 6 factorial. And now what is combination? So combination is the same thing as permutation, but the difference is that now the order will not matter. Order of the objects, order of the terms in a set will not matter. The number of possible arrangement of elements in a set, okay, possible arrangement of elements in a set is called combination. Ordered arrangement of objects is called permutation. So that is thing. Here, order is the main thing. But in combination, order of selection does not matter. And similarly, you can represent some combinations with R. And R is the same concept, which you can verify from this example 9. So we have this set S now, one containing these elements. And if we have this combination extracted from this set, and we are saying it 1, 3, 4, so then this is a 3 combination. This is called, because it is containing 3 elements. The set itself contains 4 elements, but it is containing 3 elements less than that combination. So that's why now we are calling it 3 combination. This is R combination, okay? And if you will change the order here, maybe 3, 1, 4 or 4, 1, 3, so that would be the same thing as this 3 combination is, because now order does not matter. In permutation, this 4, 1, 3 is a different permutation. But here in combination, now this thing and that thing is the same thing. Is it? Same thing. Now we have the theorem. Theorem 2. And in this theorem, we are calculating combinations. Previous theorem, we were calculating permutations. And here we are calculating what? Combinations. How are combinations of n objects of a set? How you can read it? Are combinations of n objects of a set. How you can calculate it? By using that right hand side. And what is that side is saying? N factorial divided by R factorial multiplied with n minus R factorial. So are combinations of a set with n elements. This theorem 2 has this equation in which n is what? Positive integer, r is what? Integer, and this is the interval of that r. R would be greater than or equal to 0, less than or equal to n. So now we will use this formula to calculate total number of ways, maybe if some example will come. For example, example 11. How many poker hands of 5 cards can be dealt from a standard deck of 52 cards? So you have 52 cards, and then what? You have to select 5 cards, you have to give to one person. 5 cards, give to another person. 5 cards, give to another person. So how many hands are possible? This is first question in green color. And then in yellow color, you have another. How many ways are there to select 47 cards from a deck of 52 cards? Again, you have 52 cards, and then you want to select 47 cards from those 52 cards, but how many ways are possible? So this is the second question in this example. So what is the first question? How many hands of 5 cards are possible from a deck of 52 cards? So what is n? Total number of cards is 52. What is r? 5 cards. This is for the first question. And use that formula now. N factorial divided by r factorial multiplied with n minus r factorial. So n is 52, r is 5. So combination, C is for combination. We are going to see how many combinations. So that would be, now I am opening it according to that formula. So 52 is n factorial divided by this 5 is r, this is r factorial, and this is 52 minus 5, you will have 47. Minus r. N minus r. N minus r. So this is what? N minus r. 47 factorial. Now open it, calculate it, simplify it more, and then okay. So this 47 will be cancelled, with the portion of this 52. And what will remain? 52, 51, 52 up to 47. And after that, 47 will be cancelled here with this one. And for 5 factorial, you have these values. And after further modifying it, maybe this 2 will be cancelled with this 252, 2 ones, sorry, 2 twos, and then 2 6. So there's 26. And then this 3 with maybe 57. 3 ones, and then 3 7, you will have 17, and so on. So you will have this number finally. So this is the total number of hands of 5 cards are possible with these 52 cards. And similarly, how many ways are possible to select 47 cards? Okay, this 52 is n, this 47 is now r. N factorial, this 47 is r factorial. 52 minus 47, n minus r is 5 factorial. So this combination of 52 comma 47 and this combination of 52 comma 25, this has 52 5 47, this has 52 47, no difference. You will again, if you will calculate this one, you will again get the same thing. You will get again the same answer. Because here 47 is after, 5 factorial is first. 47 is first, 5 factorial is after. So there is minor difference of just locations. Difference of locations in these two terms. So you can write it and then you can say there is no need to calculate. The calculation is already done. Otherwise, you can calculate the same thing again. And then you can say that this is the answer, that This is the total number of ways you can select 47 cards from 52 cards. Now we have corollary 2. N and R is same. And here you have R combinations of n objects of a set is equal to n minus R combinations of n objects of a set. This is just a definition. Keep it. Maybe it will be helpful in upcoming examples. Now we have the example 15. In this example, we have 9 faculty members in the mathematics department and 11 faculty members in computer science department. And what we have to do, how many ways are there to select a committee? We want to build a committee, and there are different ways to build that committee is possible. Then how many different ways? What is that total number to develop that committee for some purpose at a school? And there is a restriction for that committee. What is that? Committee should have to consist 3 faculty members from math. 3 faculty members you have to take from math, and 4 faculty members you have to take from computer science. This is the restriction. If you are going to build a committee, this is the restriction that you have to follow, and then you know the total number of faculty members in each department, and then how many ways are possible to build that committee. So you know the product rule, which is the starting of section 6.1 of this chapter, and you know the theorem 2, which just passed here, Cn n factorial, r factorial, n minus r. This is the main theorem, okay? You have to keep always in your mind. This will help you a lot, especially in this chapter. So now, this is the total number of faculty in mathematics department. This 9 is the total number of faculty. This is the n for the math. And this 3 is the condition for the math, for the committee. And 9 is the total number of faculty members in math. And then 3 faculty members we have to select from math. So this 9 is n, 3 is r. And this is what you can calculate the combinations. And similarly, 11 is the total number of faculty members in computer science, and you have to select 4 faculty members from that, which is R. So this is the combination. So this is again the same easy question, but now it has further parts in it, making things a little bit lengthy. And using the previous product rule that you have studied in section 7.1. So then what? Now these combinations, you can use this formula to calculate that thing. So which is 9 factorial, and this is n. R factorial is 3. N minus r is 9 minus 3 is 6. Okay. And then this is n, 11 factorial. This is r according to that one. Okay, divided by r factorial. And 11 minus 4, you will have 7 factorial. Okay, calculate them individually and multiply them, then you will have this answer. This is the total number of ways in which you can form this committee of mathematics and computer science department.
So when we have 2 combinations, we multiply them?
Yeah. If it is not needed that you multiply them. It is said here because the committee is the combination of math and the computer science. So that's why you have to add them, multiply them. And these are the examples that you have to consider from the book for this section 6.3. Now this last important portion. 6.4. It is about binomial theorem. It is about binomial theorem. And I'm sure that you already have heard the name of this binomial theorem. This binomial theorem has its statement. Sometimes we call this mathematical statement binomial series. That is also okay. In this series, you have two variables, x and y. And there is n, you can call it also some positive integer. And in this is the form of that binomial theorem, that you will have that x and y adding up with each other, and then you have the power of those variables like that. If you have that thing, the left hand side, if you have like that, then you can open that left hand side to this right hand side in a summation form. And here we have sigma, which is starting from j is equal to 0 to n, and then n chooses j, or you can simply say it nj. And then you have first variable x, but it has the power n minus j. And then you have the second variable y, but it has the power j. So this is the right hand side of this binomial theorem, but it is also the closed form. It is not opened yet. But we can open it by putting the value of j in this portion. By putting the value of j, we can have these things there according to this right hand side. So put the value of j as a 0 first, then we will have n, j is 0, okay, and 0. And then here j is 0, n minus 0, so x raised power n only. And then y raised power j is 0, so y raised power 0 is 1. So that's why we will get this term. And due to this sigma, we have the plus, and then we are going to put the value of j as 1. So n1, okay, n1. And then n minus j is 1, n minus 1. And y is what? y1, so okay, y. And so on. In this way, you can go on. So this is called binomial theorem. And here these x and y are the variables. And these things that you have is called the coefficients of these variables. What is this one? Coefficient. Coefficient of these variables. All these one, this one, that one, that one, that one. These are the coefficients of x and y variables. And this whole thing is called expansion of this left hand side. What is this whole thing is called? Expansion or expansion, whatever you want to say. Expansion of this left hand side. Now example we have, what is the expansion of x plus y raised power 4? So now this is the question. And now as we already know that this is called expansion, so now you know that how you can expand it. Now, so first you have, so this is something very much close to that form of this binomial theorem. X plus y raised power n, and here we have x plus y raised power 4. Okay, that's good. And now if we can expand it, and if we will expand, then this will go only up to 4, not up to n. Okay. Okay, now we are going to expand it, but first you will expand it into this summation form, and then in the next step you will expand it like that, as you are expanding it here. So okay, x plus y is equal to 4. First convert it into the summation form. Sigma j is equal to, so this is your n now. So j is equal to 0 to 4. And then what? 4 and j is okay. 4, put j as it is. And then x raised power n minus j. N is 4. 4 minus j. And y is what? J. So this is what you get from this by using this concept of binomial theorem. But this, it is not expansion yet. It is not full expansion yet. Now in the next step, you can expand it fully. Put the value of j as a 0. So then 4 0, and it will become what? X raised power 4 only, and it will become 1. Then put the value of j as 1. Then 4, 1, okay. And after putting it 1 here, 4 minus 1, you will have 3. And y raised power 1, like from here. Similarly, put the value of j as 2 in this equation. You will have 4, and the value of j is 2. And 4 minus 2, you will have the 2. And j is now 2, okay, y2, and so on. And now we can further simplify it. How you can simplify this? This is basically, this is n, this is r, according to your previous formulas. According to your previous formula of theorem 2, according to that formula, this one, this is that thing. This is that thing. So now you can compute it. Okay, 4 factorial. So this is n. So how you can write? This is n, this is r. So 4 factorial divided by 0 factorial. Sorry, it is very hard here too. 0 factorial, and 4 minus 0, again 4 factorial. So that thing will be cancelled with this one. And 0 factorial means 1. What is the factorial of 0? 0 factorial, if you will calculate it, it is always 1. So that's why you have 1 here, which is not mentioned. And you have only left with this x4. And now 4 and 1. So, okay, 4 factorial. And then this is r, okay. Here I am just changing it. 1 factorial. And then what? 4 minus 1, 3 factorial. Here you will have 3 factorial. That 3 factorial will be cancelled with this 4 factorial, and only 4 will remain here. Only 4. And here 1 factorial, okay, 1. And it is only 4 is remaining here. 4 factorial is what? 4 multiplied by 3, multiplied by 2, multiplied by 1. So 3 to 1 will be cancelled with this 3 factorial. And only 4 will remain here, which you are seeing here. And similarly, you can compute these things and you will have these coefficients here. So this is now the final expansion or expansion of this question. Moving next. What is the coefficient of x12 y cube in the expansion of this one? Now the question is changed. I am asking for the coefficients, not for the full expansion. Here you have the full expansion and also these coefficients. I can ask, what is the coefficient of x3 y? You can say 4. What is the coefficient of x2 y2? You can say 6. What is the coefficient of xy cube? You can say 4. Here, what is the coefficient of x12 y13? Of expansion 2x minus 3y power 25. From this thing, you will identify something. Here, when y is 2, this is you are getting from here. When y is 2, this 2 is equal to this r. When y is 1, that is r. When y is 3, that 3 is r. When y is 4, that 4 is 4. So these powers also giving you some idea that what is that value. So here y 13, what it means? It means when r will be 13, when r will be 13. And this expression is giving me the power is 25. This is n now. This is n or not? This is n now. Okay, now convert this expression first according to that x plus y raised power n. And then we can move on. So that's why we are just converting 2x. We are introducing plus here for that plus. And then we are moving this minus inside, minus 3y, and then power 25. Okay, this is what we have done according to binomial theorem. Okay, now this is my x, complete x. Okay, this is my y, and this is my power n according to that x plus y raised power n. Okay, now this is the format, and now we can change it into summation form. Allahu Akbar. Sigma starting j from 0 to 25. And this 25j, okay, writing as it is. This is nj. I am writing this thing. And then this is my x, 2x raised power n minus j, n minus j. N is what? N is 25, n minus j. Writing n minus j, this one. And then what? Yj. Okay, y is what? This complete is y. Minus 3y raised power j. Okay, now this is that form. I don't want to open this from the beginning to the end to find the coefficients of this x12, y13. It is not needed. It is not needed to open all that. Only this one, open that portion only. And the question is, what is the coefficient? I only have to give the coefficient. What is that coefficient? I don't have to explain other things. So that's why you know that when j is 13 and when n is 25, how you can reach that? So, okay, n is 25, j is 13. Then you can write, so this is the x, this is the variable, this y is also the variable, but this 3 inside, this 2 inside, it can be the part of, it can be not, it must also be the part of this coefficient. This is the coefficient actually. This 2 inside, this 3 inside, this is coefficient. This x and y are the variables, okay? So that's why I am taking that portion 2 only and not showing x. If you want to show x, you can show, no issue. But this, we are going shortly, okay? You can represent x here if you want, okay, represent, no issue. So that 2, I am taking that 2 only, 2 and then raised power what? 25 minus this 13, j is 13. 25 minus 13, you will have 12. And then I am taking only this coefficient, minus 3 and power 13. And now solve it using that formula. Move this minus in front. We have moved this minus symbol at the front, and then it is 5 factorial. Then r factorial is 13. 25 minus 13. So this is n minus r. 12 factorial. And 2 raised power 12 and 3 raised power 13. So this would, you can calculate finally and you can have some number here, or you can say this is the coefficient. This is the coefficient. That is okay. But if you will solve it, you will have finally some number. That would be the coefficient of this x raised power 12, y raised power 30. We can also represent x and y here, just for more clarity. But it is also clear that if we have not mentioned here, then actually that portion is related to this thing. Now we have another corollary 1. This is saying that n is a positive integer. Do you have any question in example 4 or example 2? Any question? Okay, good. When you don't have a question, okay. Something is coming into my mind, but leave it. I want to finish it. So this is the corollary now. N is a positive integer. Then sigma starting from k is equal to 0 to n, and then nk. And you know that. What is this one? This is that symbol also. That symbol. And this is the left hand side. And this left hand side is becoming equal to 2 raised power n. Now we have a little proof for that. We want to prove this corollary. What is that? We want to prove this corollary. And how we can prove it? Either we can start from the left hand side, and after using some rules, existing rules, and if we will reach at the right hand side, then finally we can say that now it is proved. Or we can start from the right hand side. We will keep on changing that right hand side by using different existing rules or definitions. And if we will reach at the left hand side, then we finally can say that now it is proved. So we have the knowledge of binomial theorem. So now, by taking that binomial theorem with x is equal to 1 and y is equal to 1, we have this binomial theorem, x plus y raised power n. When x is 1, when y is 1, so we are going to use that binomial theorem with x is equal to 1 and y is equal to 1. And then we can say that this 2 raised power n, this 2 raised power, we are starting with this one, right hand side. 2 raised power n. And then we are using here the binomial theorem, giving x 1, giving y 1, raised power n. Basically, this 2 raised power n, we can write that this is equal to this one. Can we write that one? We have changed that 2 into 1 plus 1, and then using n. So we have changed this right hand side to this thing according to that binomial theorem, nothing else. This 2 raised power n is equal to this one. Okay, that is okay, no issue. But we have converted into the binomial form to get benefit from that. And after that, when it is in that binomial form, we are now writing it according to that binomial theorem, the closed form, starting from k is equal to 0 to n, which is the power, and then nk, and then the first one is 1 raised power n minus k, or you can say n minus j, and then 1 raised power j or k, what it is according to that timetable, according to that binomial theorem. So this thing which is written here is according to that binomial theorem, nothing else. And now, so this 1 raised power k and this 1 raised power n or 1, so this, what is happening here? Cancelled. Yeah, n minus k plus k, that would be cancelled. Yes. So now simplify it. What it would what it would become? 1 raised power n minus k and this plus k. That minus k plus k will be cancelled. And then you will have what remaining? 1 raised power n. 1, whatever the power it is, it would be 1. 1, whatever the power it has, it would be 1. So that's why what is remaining? Sigma k is starting 0, n k. Here we have the 1, but not needed to mention. There's no need to mention. And that is what? That is the left-hand side of that corollary. So we have started from the right-hand side and we have reached at the left-hand side, hence proved. Now, there is another theorem. This is just a theorem you only have to remember. And this is called Pascal identity. Because it is mentioned binomial coefficients and identities. Now you are going to see first identity. First identity. Identity. There is some Pascal, there is a law called Pascal identity. And what is that identity? If n and k are positive integers and n is always greater than or equal to k, then this is some thing here written. And that thing is saying that n plus 1 k, that is something which is existing after n, because it is n plus 1. That is something existing after n. That would be equal to n. And here we have also n. But here we have k and k minus 1. So you can take this triangle. This is called Pascal triangle. You have to memorize it, okay? Or you can start it from 0, 0. And then you can say I like two-dimensional arrays in programming languages. You can take it as two-dimensional array with the loops are starting with I and another loop with j. Okay, like that, two-dimensional arrays. So here 0, 0. And then you will come far down and you will start from the left of this thing, from the left of, there is a design also in it. From the left of it, you will start from here. And you will also keep this thing here. And then you will write next after the end of this, that thing. And then, okay, after 0, 0, then it would be 1. Then this is 0th row. This is first row. This is second row. This is third row, fourth row. Just to, if you want to memorize, I'm just giving you the idea. Fifth row, sixth row, seventh, eighth. Okay, that is now clear. So this is the 0th row and 0th column, you can say. And then first row, 0th column. And then first row, 1th column. Second row, 0th column. Second row, 1th column. And now when you will start from starting, you have to write that thing before the beginning of that thing. So I'm just drawing that line. There is a design in it. And then you have to write the next in between these two things. In between these two things, you have to write the next term here. And similarly, 2, 2, after the end of that thing. And similarly, third row, 0th column, 3, 1, 3, 2, 3, 4, and so on. And now I'm going to explain that equation. And here in the Pascal identity, there is a property that this next item, you can add any adjacent terms, and then you will have the answer of those terms, the next term, exactly beneath these two terms. Exactly. So this 6, 4 and this 6, 5, what is 6, 4? 6 factorial divided by 4 factorial, and 6 minus 4 is what? 2 factorial. 6, that 4 factorial will be cancelled after with this one, and you will have 6 and 5, so 30, and divided by 2 factorial, 30 divided by 2, you will have 15. You will have 15. And 6, 5, when you will calculate the factorial, 6 factorial, I am doing the things verbally, okay? 6 factorial, then 5 factorial, 6 minus 5 is what? 1 factorial. So here you will have 6 only. 5 will be cancelled. Okay, this is the answer of after evaluation of these two terms. And when you will add them, 15 plus 6, you will have 21. That 21 would be the answer of this 7, 5. This is 7, 5. 7 factorial, and the down 5 factorial, that will be cancelled. 6, 7, 6, 42. And then you will have 7 minus 5, 2 factorial. 42 divided by 1, 21. So that is that thing. So this triangle, for example, now here, when you will add these two things, you will get this next thing. Whenever you will add these two things, this is the answer. This is the property of this triangle. Whenever you will add these two things, you will have 4, 3 as an answer. When you will add this 7, 0 or 7, 1, you will have the answer 8, 1. This is the property existing in this triangle. And okay, this is the first closed form, and after the calculation of their factorials, you have then this triangle again, just showing the same thing but with our answers, and then you can verify your answers. So when you add up and find this thing, that is called Pascal identity, and this is what this formula is explained. Now, for example, I want to calculate 7, 5, and this 7 is what? 6 plus 1. This 7 is what? My n is 6. 6 plus 1 is 7, and my k is now 5. I want to calculate this thing. I want to calculate this thing. And how can I get? I can get n is what? 6. And k is what? 5. 5 minus 1 is 4. So 5 and k is what? 6. K is what? N is what? Sorry. 6. And k is what? 5. 5 minus 1, 4. So 6, 4 is the first term. And here you can see 6, 4. And then n is 6. And what is k? K is what? 5. So 6, 5 is the second term. And after adding them, you will have the next term. This term, you will have that thing. So this is what this Pascal theorem is saying. And you have that triangle, etc., etc. Nothing else. You only have to keep this in your mind. These are the two examples of this in this section, and now it is ended. Do you have any question? Now this CO is ended. Now we are only left with one CO, CO7 inshallah, with the graphs. Any questions? आई सवाल Okay.